Well, hello and welcome. Let's look at day 2 on the chain rule. And today, got a little warm up for you to do. I want you to run through this warm up exercise and just simply indicate whether it's product rule, chain rule, quotient rule, or none of those. If you want to say power rule because that's what you'd use, that's fine. Shouldn't take too long. There are 12 problems. So for instance, on number 1, I can see that we are taking x and multiplying it by sine x. So I would need to use the product rule to take the derivative of number 1. Walk through 1 through 12 quickly, hit pause, give yourself some time, and then I'm going to flip forward so you can see the answers. All right, here, ooh, it didn't go forward. Here are the answers. And just take a look to see if you agree with me. Lots of chain rules spread throughout here. There were only a couple product rules. Um, this one is not a product rule because remember e squared is just a number. So all I would need to do is take the derivative of sine and give me cosine. So I'd have e squared cosine x. This one here would have been power rule, so that's why I said none on it. And let's look at this one. I could have thought of it as 1/8 times that polynomial, that is the numerator. And so it would have really been a power rule. All right, following on the bottom, you have problems 13 through 17. I would like you to give those a try, a little bit more work on them, a lot of chain rule, and then I'm going to push forward so you can see the answers. Any surprises there? The one that might be a little difficult is the one that's written in function notation. It's g of some stuff. So I can see that this is my outer function, and then this is my inner function. So I take the derivative of the outer, leave the inside alone, and then take the derivative of the inside, and that's how I got my answer. Little chain rule there. All right, that brings us to day 2, 3.1-B, worksheet for homework tonight. So we're going to take and delve into natural logs and e's using chain rule. What we worked with earlier in chapter 2 was the simple version of natural log, the derivative of natural log x. Now, and we knew that that gave us 1 over x. What happens though if we have some function that's a little bit more colorful than just x? Well, if we would indicate that by just saying it's u, where u is some function, and the rule for that becomes 1 over u, which is quite similar to what we had here, 1 over x. So 1 over the argument inside the natural log, and then times the derivative of that inside piece, so the u prime. Some people memorize this as u prime over u. I probably will spread it out over 2 steps today just so you can clearly identify what was the 1 over part and then what was the chain rule piece coming in. What about absolute values? We have seen sometimes where they write the absolute value into the natural log to ensure that your expression stays positive. If that's the case, the derivative still looks the same. It's still u prime over u. We know that u cannot equal 0. However, u could be whatever it wanted because of the absolute value embedded in the original problem. Logarithmic properties that you learned in Algebra 2 can come in handy. And just a quick review of those 4 natural log properties that actually work on any log, whether it be log base 10, log base 8, any log property. The natural log of 1 or the log of 1 turns out to be 0. That is because e to the 0 gives me 1 if I think about it in exponential equation format. What if I had 2 functions multiplying each other? This could create quite a fun derivative because I'd have 1 over u for the natural log part, and then I'd have the chain rule, which would take the derivative of a product. So then that would swing me into product rule. Sometimes it's a little faster if we use our natural log properties from algebra to make 2 separate natural logs, and then it's just going to be like u prime over u rule for derivative. So just to remember, if I have the natural log of 2 things multiplied, it's going to give me the natural log of a plus the natural log of b. What if they were dividing? natural log of A over B. Well, if it's a quotient of two things, we can separate them using subtraction. So those rules do come in handy. The other one I want to point out that often is utilized is natural log of A to the n, where n is some power. We can use the power rule, which allows us to swing that inside power down in front of natural log. And then you can see, then you've just got a multiplier, a constant multiplier, and we would take the derivative of just natural log A. Let's try it. There are 4 or 5, 6 examples in this first part, so let's run through them. Find the derivative of each. Well, I recognize this as u, and it's no longer just a simple x, it has 2x. That'll prompt a chain rule. So I'm going to write y prime equals 1 over u times u prime. That's the recipe that I'm going to use, and I'll have y prime equals 1 over 2x times the derivative of 2x. Well, the derivative of 2x we recognize to be 2. And putting it together, I can cancel the 2, so I finally get y prime equals 1 over x. B, we get the absolute value in there. Not even thinking that the absolute value would really be necessary because I don't have a chance for this inside argument to ever be negative if I'm squaring x. But that's all right. We do treat it just the same. So I'm going to treat this as 1 over u times u prime. And y prime equals, this is my u here. So outer function, derivative of the natural log will place this as 1 over u, or 1 over x squared plus 1. I don't need absolute values on it. Times u prime. So that's going to be the derivative of that inside function. So y prime will equal 1 over x squared plus 1. Derivative of x squared plus 1 would be a 2x. And finishing this one, I would write it as one nice fraction brought back together. And the rules for multiplying fractions would be numerator times numerator, denominator times denominator. For C, let me shift up here a bit. For C, I pick up a product rule. I see two things multiplying here. I'm going to apply the product rule. And then within the natural log is sine x. That's going to have a derivative of itself too. So we have product rule and a little chain rule going on. Remember our product rule, I'm going to use f's and g's on this one, will be f prime g plus g prime f as our guiding principle in taking this derivative. So I get y prime equals, the derivative of x squared would be 2x multiplied by natural log of sine x. We leave the g alone on that one. Added with the derivative of g, well now inside that natural log I see a u, so this will be 1 over u, 1 over sine x times the derivative of sine x, which is cosine x, multiplied by f, which is our x squared. So this is the f piece. This is all g being taken. Now the last thing I should do is probably make it look a little bit nicer if I can. And I'm not seeing a ton of things to do other than write that fraction at the end a little bit more concisely. So I would say I've got x squared cosine x divided by sine of x. Could you condense this down into one fraction now? That is a skill that I expect you to know. And to do that, I need to make like denominators. So I would introduce, and if you've got a different color pen, use it because it'll help you see that you inserted something a little bit unique there. I'm making like denominators here, right? So I get 2x natural log sine of x. I'm going to keep parentheses just because I think it is more clear. I've got times the sine of x. You know what? I like that to be up front, so I'm going to write 2x sine x natural log of sine x plus x squared cosine x, all divided by common denominator of sine x. And that's probably what you would see on a multiple choice question in the AP. The only thing that I could see in addition to doing would be to pull out an X GCF that fall all the way forward. But I'm going to trust that you can do that algebraic skill on your own. D. Well, this inside piece becomes my U. If you have a highlighter, just think of all those avid strategies, marking up the text, using different colors in your notes to help clarify things for you so that you can follow your work and kind of repeat in your mind what was going on when you took these notes. This is my U. So now, what is the pattern for a natural log? Well, the pattern for a natural log is 1 over U times U prime. Got to have all this stuff memorized. All right, so H prime of T equals 1 over U, so 1 over negative T squared plus 9T multiplied by the derivative of the U, which would be negative 16 T squared plus 9. Now, would there be anything wrong with you writing that piece above it? No. Learn how to take notes so that it benefits you when you come back to utilize those notes. So negative 16t squared plus 9 over negative 8t squared plus 9t. There we got it. Taking natural logs, not so hard. I say that, and then we end up with these problems. Look at this one. Wow. It's got the square root inside it. I see 3 levels here. I've got a natural log as my outer function. I have the square root next as a middle function. And then I have the u part as x squared minus 9. I need to take the derivative of all 3 steps. Or do I? Maybe I could get it down to 2. And I can if I use my algebraic log properties. So I'm going to write algebraic log properties. Oops, let's spell it right. And here's what I'm going to do. I'm going to think of this as the natural log of x squared minus 9 to the 1/2 power. Now use the power rule of logs to swing that half in front. So I get g of x equals 1/2 natural log of x squared minus 9. Oh, you think there's still 3 levels? No, not anymore, is there? We have really a multiplier, a constant multiplier, which are easy to deal with. Just pull it out front, do your derivative, put them back together. And now I've just got a u inside my natural log. So let's go into taking the derivative. We're going to have u prime of x equals our multiplier, 1/2, stays out front. I get 1 over u, 1 over x squared minus 9, times the derivative of u, which is 2x. And there's our result. Now, simplify this. This is what I'm doing. I'm simplifying here. Here I took the derivative, which you should know anyway because look at the notation, right? G prime of x. It changed. It went from g to g prime. Alrighty. Ooh, 2's are going to cancel, aren't they, as I simplify it? I'm going to get x over x squared minus 9. Fantastic. Not too bad if you remember to use your log properties. All right. Oh, I know what I was thinking. As I was going through this, I was wondering how many of you indicated this was our 1 over u, this was our u prime. Oh, I was thinking of multiplying. There we go. So if it helps your notes, put it in there. Next, let's move me. Next, the derivative. This means to take the derivative of the inside stuff of the function. Our inside function's a bit complicated. It has a quotient going on. Oh, yay. I'm not a particular fan of doing the quotient rule, so sometimes I'll try to get around it, and I'm going to use those algebraic log properties to do it. I hope you write that down too, because it will just help you realize how come we are allowed to do natural log of t minus natural log of t to the third, right? And we want to take the derivative of this stuff. So I'm going to embed that in brackets and show that we're going to take the derivative with respect to t. Oh, that's kind of a new twist too, isn't it? When have we been working with t's? A little bit, but not a lot. So this just tells me my independent variable has now shifted to t rather than x like we were seeing in problem F. Okay, so I can just take each individual log, can't I? But before I do that, I'm kind of thinking power rule on this. And that would allow us to sweep it down in front. So I'm going to use power rule of natural logs to do that. Not derivative power rule of natural logs. All right, let's swing through this and do it. Now that I've got I'm into taking the derivative, I'm going to rewrite my left-hand side of the equation to be either y prime, or I could use dy dt like Leibniz would have. And I'm going to write this as 1 over t. Okay, and since we're with respect to t, that works. And it's just very simple. It's just a 1 over u. This t came down in front, so now I have to this is a coefficient, and I need to take the derivative of t. I'm going to indicate it in that fashion so that I get one more line that you can follow the work quite clearly. 1 over t minus multiplier. Derivative of t is simply 1. Do I really need to write it? Nope. dy dt equals 1 over t minus natural log of 3. Could you put this together as one fraction? I hope you can. That is an algebraic skill that should be easily available. I would just simply need to multiply by t over t, wouldn't I? To create a common denominator of t, and then I would end up with 1 minus, I'm going to put the t in front of my natural log of 3. And there would be. So what would be acceptable on a test? Either that line or that line. Very good. All right, next, derivative of exponential functions base e. So earlier, we really focused on what the derivative of e was. And you guys got very good at that, knowing the derivative of e to the x is e to the x. What if we made this a little fancier and had e to a function up top? Then what? Yeah, you guessed it, the chain rule kicks in. So if I have e to u, where u is some function, I'm going to have it is itself. The derivative becomes e to the u, and then I have to chain off and take the derivative of u. So one easy way to write it is e to the u times u prime. Okay, so in A, this is my u. The derivative piece is going to end up being e to the u times u prime. Maybe even practice that in homework tonight, writing out the rule first, then applying the rule. So I'm going to get e raised to that u piece, set up a parenthesis because this gets multiplied by the derivative of 2x cubed minus 3x. And the derivative of 2x cubed, well, you know what, I'm going to write it and give you a separate step. I need to take its derivative, so I'll indicate with the prime symbol, and I'm going to have the derivative of this would be 6x squared minus 3, which needs to be in parentheses because both terms have to multiply by e to the 2x cubed minus 3x. Yes, did I change the order? Yeah, because I knew that I would like to have this stuff out front. So that's the derivative being taken there. And that's fine to leave our answer right there. Part B, you know what? I might prefer to see this as e to the x raised to the 1, negative 1. Yeah, I think I'm going to like it that way. So now I'm recognizing this as my u. All this flexibility of thinking, right, where I can do multiple representations of the same thing is important in calculus. So we know the pattern. It's e to the u times u prime. Y prime will equal e to the 1 over x times. Now what's the derivative of x to the negative 1? Well, its derivative is a negative 1 comes down, and then it goes to a negative 2. So I have e to the 1 over x multiplied by negative 1 x to the negative 2. And now let's just clean it up a bit. And I get y prime equals Well, it's definitely negative. The x to the negative 2 will drop to the bottom. The e stays up in the numerator, right, because that's like over 1. And I think that looks about as concise as it can be written. All right, C. Well, C actually could be quite easy. Do you see any variables? I'm giving you time to write that down. I see none, right? No variables. So that really is just a number, isn't it? This is f of x equals some number. And the derivative of a number is 0. All right, game over on that one. Next one, I hope immediately what went in your head? Quotient rule? Yes, great. All right, so we are going to have quotient rule, and we know the pattern for quotient rule. It's f prime g minus g prime f over g squared. So I'm going to think of this as my f, this is my g. Each of them have a little inside piece, a little u inside them. So let's get to it. K prime of x will be f prime g minus g prime f over g squared. Keeps marking with my knuckles. All right, so k prime of x will be, well, the derivative of e to the 4x will be e to the 4x. The derivative of 4x is simply 4, and then we have to multiply it by the bottom sine of 2x. You get really good being creative with your parentheses and brackets, right? To help distinguish between different things. Next, I need to take the derivative of sine of 2x. Derivative of the outer gives me cosine. Leave the inside alone. So cosine of u times u prime, derivative of 2x is 2, times the top, e to the 4x. All over bottom squared, so sine of 2x squared. We've done the derivative. This would pass on the AP test if it was free response. Doesn't quite pass for my test, or probably any professor's test in college. They will expect you, and I expect you, to simplify or make it look a little bit nicer. I do notice it has some things in common. Let's use a highlighter. I have e to the 4x, e to the 4x. Sweet, that can be pulled out front. Anything else that you see in common? A factor of 2. 2 goes into 4, doesn't it? So what we're going to pull out front will be 2e to the 4x. And then I'm going to use a bracket. And I'm going to indicate that this was a GCF. And I think you should do that too. Now, inside, I pulled out 2 from that 4, so I will still have a 2. Remember, I got to make a multiple, or it needs to multiply to make 4. 2 sine 2x minus, well, all of the 2e to the 4x came out front, so I simply need cosine of 2x. Bottom denominator, can't do much about that. That's going to stay. If you'd rather write your squaring right there, that works too. And then you don't have to use quite so many parentheses. One thing I would kind of sweep this back through. Does it get you back the numerator that we had done in the preceding step? Yep. Okay, moving on. Oh, so much. We have, just the bottom part. Derivatives for bases other than e. Oh, this is just to go through some of those rules that we've covered earlier in our lessons. We knew the derivative of a to the x, like the derivative of 8x. Its derivative would have been natural log 8 times 8x. Well, now they're saying, what if I had a to the u, like 8 to the 2x, where it's no longer just a simple little x? Well, then I'm still going to have natural log of 8 times 8 to the 2x, because it has itself. And then I need to take the derivative of the 2x piece, getting us the 2. So the derivative of that, very easy example there. Log with a different base, we remember the log with a different base is 1 over natural log of a, where a is coming from the base, times 1 over x. 1 over natural log a times 1 over x, because the derivative rule for logs is 1 over x. Now, if we amplify this a little bit and make this, maybe this is 8x plus 2 now in there, where it's no longer just the simple little x, we've got to get a little bit broader scope on the derivative. So it's still 1 over natural log a, got it. It's still 1 over u, yep, and then it's chain rule derivative of du dx. So this could be seen as u prime over natural log of a times u. All right. I'm going to go down to the bottom. You can read that other one. That's just algebraic notation stuff. Find the derivative of each of the following. Okay, so I recognize that I've got a y equals a to the x. And I know the rule for that, y prime would equal natural log of a times a to the x. That should be pretty easy. So y prime in this case is going to be natural log of 2 times 2 to the x, and that is done. Because the x is a simple case, we don't have to do a u prime. If we did a u prime, derivative of x is 1, and it goes away. Now, once again, I'm recognizing this as an a to the u. So my derivative pattern is going to be natural log a times a to the u times u prime. Let's put our stuff to the test here. So what is my a? It's a 2. So I'm going to have natural log of 2 times 2 to the 3x times the derivative of 3x, which gets me 3. Do I want to rearrange a little bit? I think if I rearrange this, I can get by with no parentheses. Oh, that's not going to quite work there, is it? Yeah, I think would be more clear if I did choose to use a parenthesis in there. So something like that. If you were thinking you were going to go this route, I think that would probably even be maybe a little bit better. I wouldn't necessarily have to have those parentheses there because it will set aside on its own. Then I end up with all the coefficient, the multiplier stuff out front, which I kind of like. All right, C, analyze it. What do you see? Well, what I see is a log with a different base of u. And the pattern for that is, I gotta think about it, 1 over a natural log of a times 1 over u times u prime. Okay? Now let's take its derivative. So we get y prime equals 1 over natural log. What's the base? Go back to your original problem. Base is 10. Times 1 over u. This is our u. So 1 over cosine of x. Now what's the derivative of cosine? It is negative sine x. And the reason I decided to go with a parenthesis is because without parentheses, it's going to look like I'm subtracting sine x. And I definitely am not subtracting. This is all held together with multiplication. So always, always think about how the interpretation could be made. Doesn't always end up quite like you think it might have when you step back and take a glance. Cosine x. Now, did it strike you that you've got sine over cosine? It did to me, and I know what sine over cosine is. It's tangent. So I'm going to write this as negative tangent over natural log of 10. I would say the AP would have either an answer like that or an answer like that in their multiple choice. All right, log base 3. See if you can do this one on your own. Hit pause. Go do it. All right, I will do it too. I'm going to get y prime. if I get a pen that writes, I'm going to have y prime equals 1 over natural log of a, which is 3, times 1 over u, which is negative x squared minus 6x, times the derivative of the inside piece, which is going to be a negative 2x minus 6. Sweet. That's going to give me a y prime. Now, just make it look pretty. I'm going to pull out a negative 2. I'm going to have x minus, I'm going to have x plus 3, excuse me, so that I get the negative 2x minus 6 there. On the bottom, natural log 3 multiplied by negative x squared minus 6x. Are these parentheses necessary in both cases? Absolutely yes. That takes us to the homework, and we are done with part B. Have a great day.